Okay, let's get started. This webinar is on best practices for secure access of third-party APIs from mobile apps. It's a long title, but a very interesting topic. We had a lot of people signing up for this webinar. So it's obviously a topic that is of some concern in the community. We'd like to welcome you wherever you're calling in from. And we have a very interesting agenda for you today. We have two speakers. We have Richard Taylor, who's the CTO of Approve and the co-founder, and Skip Hovsmith, who leads the US team for Approve. And they're going to be talking about how we can jointly eliminate hard-coded API code keys from mobile apps. Now, you can ask questions at any point. You put them in the question channel, which is open now, and we will get to them. Either during the presentation or at the end. And we do encourage you to stay till the end because there's a special offer at the very end that we will make. So stay on to the end, and then you'll be able to see that offer. And I think you'll find it very interesting. So that's all I have to say. At this point, I'm going to hand over to Richard and let him start the presentation.
Hi everyone, so I'm Richard, I'm CTO of Approve. So we're going to talk about this kind of topic in general terms, aspects of secure access. Then we're going to talk about how Approve fits into that picture, and we're going to talk about a new feature of Approve which we're introducing called Runtime Secrets Protection. And then, all being well, we're going to hand over to Skip, and Skip's going to do a live demo, and then hopefully at the end we'll have a bit of time to answer any questions that you have. So sort of in addressing this topic, I mean, one of the things to be concerned with is API keys. So API keys are the mechanism that is typically used to be able to access a backend API. So normally when you use a third-party API or any API, you sign up and you get some kind of key, which is essentially it's a random string. It's essentially like a password. And in effect, this kind of authenticates the app that's making the call so that the API backend knows that it's this particular app that's making a call. And that's used basically to block any anonymous traffic that's trying to use backend API. It can be used to limit requests. There's normally some kind of quota associated with a particular API key. And there might be some kind of permissions associated with the API key as well. So although it's a sort of an identification mechanism, in practical terms, you do have to consider the API key to be a secret, because if that API key becomes known, then essentially your app can be impersonated and API calls can be made on its behalf. There's often a kind of debate about whether API keys should be used all the time, and there are mechanisms which allow you to use access tokens instead. So one strategy actually is to have an access token which is associated with a particular app and maybe a particular user, and you obtain that access token when the app is first installed. And this can also be associated with user authorization. And there are mechanisms in OAuth 2 to allow you to do this kind of thing. So basically you can do an authorization at the start and then obtain an access token that could be used to access an API. Not all APIs support this approach. So this has some validity because it sort of ties the access down to an individual user. But the problem is, in many applications, it's actually quite easy to sign up as a user. So if it's just based on user authorization, then essentially you're not actually authenticating the app. You're just saying you have a user. So in that sense, it's not a particularly strong protection. So then you get to the situation where you're talking about using a client secret in order to protect that initial request, and essentially you're back to the same problem. So instead of having an API key, you have some kind of client secret, but again, it's something that needs to be protected. So there's quite a lot of discussion about, well, what can go wrong if API keys are exposed. I mean, this is a general problem. It's not just to do with mobile apps, it's also to do with server-to-server communication. There have been various cases where developers have checked in API keys accidentally in source code, and then of course there are various tools out there that can look at source code, find those API keys, and then abuse them. So this is an issue that has been talked about quite a lot. There have been particular attacks associated with this. And in the last couple of years, we've seen more and more tools that enable you to find API keys that you might have accidentally put in source code. And there are various other sort of secret management capabilities out there that allow you basically to separate secrets so that they're not stored in your source code. Essentially, you need to keep them separate. Use some kind of secret manager to keep them separate from source code itself, so the source code isn't a leak. But the problem is, in the case of mobile apps, you have the problem that you have to publish an API key essentially as a public client inside the mobile app. So what kind of strategies can you use there? So although you may have kept your API keys out of your source code and used some kind of secrets manager, at the end of the day, you're basically compiling those keys either into configuration or into code, and then you're basically releasing the app into the App Store. So it's still there. So if we look at sort of third-party API access from mobile apps, this is just kind of an overview of what's happening. You compile your app, you publish your app as an APK or IPA on iOS. This gets pushed to the App Store. So essentially, it has these embedded API keys or other secrets inside it. And then as the app runs, it can basically use those API keys to access whatever APIs your app is dependent on. These are just some examples of third-party APIs an app may be using. We've done a survey recently that shows in general that individual apps are dependent on a large number of third-party APIs. So whenever it accesses that individual API, that API key is extracted from the code as it runs and then transmitted over the wire, typically over TLS, but is transmitted to access that backend API to basically authenticate that it is this particular mobile app making the access. So the issue here is that there are various vectors that can be used to extract those secrets from the mobile app. I've put some example tools at the bottom here. So one possible angle is that you can extract the secrets directly from the published app itself. So there are various tools, MobSF being a good example, which is basically a static analysis tool, which can take an APK or an iOS IPA, essentially reverse engineer it. You can use this for code extraction too, but also it has various analysis patterns that it uses, tries to find things in the code that look like API keys, and basically will present you with a list of potential API keys that might be embedded inside the app. There's a really good tool from CloudSec, which is basically a search engine that does a similar thing, allows you to see source code, see API keys, and there's got command line tools you can use, like APK tool to reverse engineer Android apps, and just grep on images. We'll often find API keys. They tend to be quite easy to find because they have certain characteristics and kind of high entropy, so they sort of stick out in the code. And of course, once you have those API keys, you can then make a direct access in a script. So there's that angle. There's also the angle that at runtime, the API keys are going to be in memory. So there are various hooking tools that you can use, like Exposed or Frida, if you're running on a rooted device, to basically hook the app, hook particular function calls, collect the API keys as it's running. Again, then you can use it to access backend APIs. And then finally, there's also this angle of extracting these API keys or other secrets via a man-in-the-middle attack. And there's tools like Bitter Proxy and Charles Proxy, etc., that allow you to do this. So I'm going to talk in a little bit of detail about how the man-in-the-middle attack works, because I'm going to come back to that aspect later, because that's something we cover in a proof. So normally when your app makes a connection to a backend API, it's obviously doing that over TLS. So the channel itself is encrypted. And if it's going to a particular API named address, then it's looking to see a valid certificate coming from that API backend. that ultimately has a chain of trust that leads to a root certificate, which is basically trusted by the device. So the device itself has a series of root certificates on it that are basically the trusted root certificates, and all certificates that it trusts have to lead back to that. So that normally maintains the sort of integrity of that channel. And once the communication is established, then it's over TLS and it's not possible to decrypt that traffic. However, what you can do with one of these proxy tools is basically you can insert yourself between the app and the backend API. And the way that becomes trusted is that if the device is rooted or jailbroken, then you can basically push a self-signed certificate from the proxy tool into the device, and then it becomes trusted like anything else. So all of a sudden, the app is quite happy to connect to what it thinks is the actual backend API, but it's actually a man in the middle impersonating that backend API. Then the traffic can communicate through the man in the middle to the actual backend API. But of course, in between, the attacker can see all the traffic and can also extract the API keys. So, I mean, what are the risks of stolen API keys? Obviously, it depends a lot on the capabilities of the particular API and what is allowed given the permissions you have for an API key. So there's various different angles here. I mean, there's the possibility that having access to an API key outside of the app allows some data exfiltration, either directly or sort of indirectly through things like OWASP, excessive data exposure. So one of the kind of classic issue with APIs is that they provide a lot of data, but only some of that data is presented in an app, and it essentially relies on the fact that the app isn't presenting all the data for the security of the remainder of that data. Once you have the API key, you might be able to access it directly and therefore see all the data, perhaps running it in Postman or something like that. There's also the possibility that there are API keys associated with crash analytics or install analytics, etc. And you can use that to basically impersonate the app and post incorrect data, undermine the analytics. There's the issue that generally, you have any kind of API key on the back end, then there's going to be some kind of quota associated with it. So you can't make an infinite number of API calls. There's going to be a certain number of API calls that you could make per day, perhaps. And if that API key is extracted and bots or scripts start making those API calls, very quickly your quota could be used up. And that could be used as an act of vandalism, in effect, a DDoS attack, because essentially what happens if that occurs, then the quota is used up and the real app itself will be rejected and effectively won't be able to function because it won't be able to get access to backend APIs. And if you have some backend APIs that are pay for use, then there's a possibility that if API key is extracted, then some freeloader could be using that API key to get access to your API on your account, and therefore using up some of your paid quota. So in terms of protection, there are a number of different angles which are typically used. I've kind of presented three here. One is obfuscation or code hardening. So this is really a protection against static reverse engineering. So the first case I talked about, where you just simply download the app out of the App Store and then use tools to statically reverse engineer keys out of the app. So if you obfuscate the app or harden the app in some way, then it becomes much more difficult to do that because those keys may be they're obfuscated or encrypted in some way and may only be in their kind of plain text form when the app actually runs. So that's a good protection against the first line of attack. But the problem is that it doesn't protect it directly against the runtime or man-in-the-middle extraction attacks. And the protection is only as good as the weakest link. Pinning is also used as well in apps, which is essentially a way of saying to the app, only trust certain certificates when you make a connection to the back end. So this essentially stops the man-in-the-middle route being used directly. However, The problem with that is that you can still, even if your app is using pinning, it is still possible to defeat it if you use certain hooking tools running inside the app if the phone that's running on is rooted or jailbroken. So really that only works if you also have a kind of strong runtime application self-protection mechanism running inside the app as well to prevent that style of attack. And the other approach that is taken is to basically move the API keys out of the app entirely by communicating with the backend via a proxy rather than directly to the API. So the idea here is that rather than the app connecting directly to some backend API, you set up some kind of proxy in the cloud, which the app actually connects to. The app authenticates itself to that proxy, and then the requests get forwarded on to the actual backend API. So in that case, only the proxy itself knows the real API keys, the real third-party API keys, and relies on the authentication of the app to prove it's the app, and then to make those backend API requests. The problem with that is that, of course, you're adding a bit of complexity here because you're adding latency to all the requests. You're adding cost because all the requests are going from a proxy. And of course, you have to then worry about the resiliency of the proxy because, of course, if the proxy goes down, then nothing works. So there's some issues there. And also, in some ways, it just moves the problem because, of course, well, how do you authenticate the app against the proxy? You're back to having some kind of API key or secret. And of course, if that can be extracted, then an attacker can just go against the proxy and use up all the quota on the proxy. So you have to be careful whether you're actually solving the problem there or just moving the problem. Although it is nice to be able to control all those API keys in the proxy itself rather than having them inside the app. So that's sort of the background to this kind of problem and how it relates to mobile apps. What I'm going to talk about now is Approve and how Approve has worked up until this point, because I'm going to then move on to talking about the new features that we've added for third-party API protection. So currently Approve, which is has been released since 2017, is a kind of API protection and app protection tool that is a combination of an SDK and something that sits in the back end. And this has primarily, to this point, been focused on protecting first-party APIs, so APIs that you may control. So as an app developer, there may be some third-party APIs you're using, but there also might be APIs which are on the back end that you control directly. And what Approve is about is protecting various attack surfaces. So it's about proving app integrity. So rather than using a kind of API key to prove the presence of a particular app, it uses a signed token approach, and it's proving that app integrity. It's also looking at the device itself to make sure that there's nothing nefarious going on in terms of hooking or any exfiltration that might be going on to hook the app. And it's also looking at the attack surface of the API channel itself. Obviously, you're communicating over TLS, but this is about making sure that there can't be any man in the middle. So to give you an overview of the architecture of Approve, this is sort of a 5-step flow of how Approve API protection works, protecting a kind of first-party API. So you essentially develop the app as normal, but there is an Approve SDK that is integrated inside the app. So you build the app with the SDK inside it. You get a APK or Android app bundle or an IPA on iOS, and that gets pushed to the App Store. And essentially at the same time, you use a command line registration tool that basically registers that particular version of the app against your Approve account, so that we know it's a valid version of your app. There's various other parameters that you can set in terms of your security policy, etc., that you want to see on your apps that you administer and approve. So as well as the SDK part of Approve, there is a cloud service. And so essentially what happens is that when your app runs, it will make a call into the SDK, and then the SDK will send a load of sort of heavily defended measurements that it's making about the app environment and the device environment. So it basically sends this information about the app and device integrity measurements to the Approve cloud, where those measurements are evaluated against your criteria, making sure it is a valid app, etc. Looking for things like routing and jailbreaking, various other things. Then the Approve cloud will make a decision, and then will send back a short-lived JWT, so the JSON Web Token, a signed token, back to the Approve SDK. So each Approve account has a different signing key. So that signing key is inside the app, it's inside Approve, so it will send a signed JWT back. Essentially, it has two responses. It can either send a valid JWT back if it's happy, and everything seems okay. If it's not happy, then it won't send a valid JWT back, which means the app then can't proceed to make API calls. So the JWT goes back into the running app. And then through our quick start integrations, which I'm going to talk about later, basically when you make the API calls, that JWT is added automatically to the requests. And those requests are made over a pinned version of TLS to make sure that there is no man in the middle. And then it goes to your backend API. And the change you have to make on the backend API is that basically you need to check that the JWT that you're receiving is valid, which you do by basically checking its signature against the signature for your account. This can either be a symmetric signature, depending on the style of JWT, or we also have public-private key pairs. So there's a private key inside Approve and then a public key that you can use to check on the JWT side. And if all checks out, so you've got a valid token, it's inside the 5-minute lifetime, then you can let the traffic through. And there's an automatic process that goes on that if your app's running for more than 5 minutes, it automatically refreshes it. So what we're doing in terms of the app and environment checks, various things, which we're always adding to. So routing, jailbreaking, various hooking frameworks, emulators, simulators, various things that might be going on inside the memory map that indicates that something might be happening with data exfiltration, whether a debugger is attached, what is the actual app, layout, is it actually the app that you registered? So essentially, these are all good positive signals to show that it is really the correct app that is making the access, and therefore that will get the valid token. And as a side benefit, in effect, because the app is communicating with the Approve cloud, we see at runtime all the connections from various different devices, and you get live metrics and various rolled up metrics showing you what's actually happening in your app environment, the amount of activity that's going on, but also if bad things are detected, what are those things, and various tools that allow you to do more kind of deeper dive analysis of these things. So this is great for first-party APIs where you control the API, because in order to use this mechanism of using a signed token, you essentially need to change the backend API to do the token verification. However, there's still a challenge around third-party APIs. So if your mobile app is communicating directly with the third-party API, then the challenge here is that that third-party API is probably authorized via a API key, and maybe an access token as well if it has a kind of user authorization element to it, but it's not using an Approve token. So, and you can't modify that backend. So if you want to communicate it with it directly, you can't add the Approve token check. And also the certificate pinning part can't be added so easily, because certificate pinning is essentially saying, I am expecting this very particular certificate on this backend API. And if it's a third-party API, you're not controlling that. So it could change at any time. So you really can't pin against that kind of API backend. So we have various customers who've taken Approve, and they've used it also, as well as protecting the first party API, also as a kind of proxy solution. So one of the things you can do is you could use the Approve token to validate that the access is really coming from a correct approved app coming from the right environment, and then go out to third-party APIs. But of course, that does have the latency and cost and resilience concerns. And also, we find that there are various mobile apps out there which essentially have no custom backend. They're all using third-party APIs, and therefore, mobile app developer doesn't necessarily want to deal with the backend aspect at all. So this is why we've introduced this Approve runtime secrets protection. So this is a slightly different model of using Approve. It has all the same protections, so all the things we're checking for it is exactly the same. So you go through the same process of including an Approve SDK, you register the app, but the additional thing you also do is that if you have secrets or API keys inside your app, then you can register them with Approve, and they essentially then get stored securely inside the Approve cloud. So they are no longer inside the mobile app at all. They're taken out of the source code, they're taken out of the compile code. They don't exist at all in the mobile app at the point it first starts. So the idea is that the Approve SDK does the same thing. It does its app and device integrity measurements. But then if the app checks out okay, then those API keys are kind of sent just in time to those valid apps. If the app doesn't check out, then the keys aren't sent, and there's a mechanism basically to inform the user that this isn't actually a proper instance of the app, or it's running on some kind of compromised device. So you can feed back to the user, but essentially then that particular app instance doesn't get a copy of those keys. And then the same sort of mechanism is used in that we can run with the networking stack, add API keys automatically, and they're sent over a trusted TLS route to the backend APIs. So essentially this means that only valid app instances can access those API keys, and therefore those backend APIs. The way we deal with the pinning issue is that, as I said before, we can't directly pin against a particular certificate in a backend API. So the way we deal with that problem is that in addition to the device trust store that's always there and is potentially subject to compromise, when you use Approve in this mode, we have an approach called Managed Trust Routes, which essentially means that we have a copy of the trust store inside the app. And so we'll only make the connection if it passes the device trust store and it passes the trust store which is inside the Approve SDK in effect. So the standard man-in-the-middle route doesn't work because essentially you can't compromise the connection because the way we protect the networking stack, it won't allow that connection to occur. These trust routes are dynamic, so essentially they can be changed at will and then dynamically updated inside the app. So there is a mechanism to basically control those trust routes. If you want to remove particular certificates or add new certificates that have been issued, then we can do that dynamically without any need to actually update the app itself. And in order to make the integration of all this straightforward, we have various quick start integrations on the front end. These are all the overall frameworks that we currently cover. The standard Approve integration is available for all of these. We are working on a few of them still in terms of this runtime secrets protection. That'll be coming soon in the course of this month. Within Android and iOS native, we actually have various different variants. So there are various different networking stack choices that you might have for native apps, and we support a large number of those. Have a look at our website. So the sort of approach that we take is that we try and make this as simple as possible by providing a networking stack that has exactly the same interface as the standard networking stack, except that it adds this approve and secrets capability, and also adds this connection trusting. So what we ask you to do is basically, if you have some kind of secret in your app, which is in the configuration or in the code, then you basically change out that secret for a placeholder value. So it's not the actual secret used to access the API, but some other innocuous string that's of no direct usage. And then our networking stack does a interception on the fly in effect. So basically, if you're providing the API key as a header, then it will detect that API key is there. It will go out to approve, and if the app checks out, then it basically makes a replacement, puts the secret in, and then the actual request is made with the secret. So this is all kind of done in memory. It doesn't need to go out to approve every single time for every API request. It kind of securely stores those secrets in memory for a short period of time until there's a refresh requirement. But each time you access them, it is actually doing some analysis of the environment that the app is running in. So if you suddenly attach a debugger or something like that, that will be detected. So we can do that with headers, and we can also do that with query substitution. I mean, some APIs provide API keys as a query parameter on the URL rather than as a header. So we also support that. So you can basically pass in the query parameter. We will then do an interception on the fly and rewrite the request. So it's actually got the secret at the point it goes out, and making sure that it's all protected from a kind of TLS and no man-in-the-middle interception point of view. And obviously, if there's any attack on the device itself that indicates there might be some hooking, then the app wouldn't get the secrets to start with. There's also a further thing we can do, in that at the time a new app instance is connected, we actually assign it a per app instance secret, which is then securely transmitted down to the app, and we can actually use that to encrypt securely strings effectively inside the persistent storage of the app itself. So it means that if you have some kind of long-lived access token, that can be encrypted by this mechanism. So when the app restarts and reads persistent storage, it still needs to go through the process of its verification to prove it's still running on a valid device and nothing's been added to the device or the app, which is bad. And only if it passes those tests will it be allowed to have its encryption key in order to decrypt that data. So in summary, so this approach means that you no longer need to hard code API keys or other secrets in the mobile app. So it removes that concern of reverse engineering. It deals with all the points where you might be able to extract those secrets. So it's using a sort of app attestation approach to ensure that only a real app on a valid device can access the API, and we're dealing with channel integrity. And the other advantage, of course, is that because the secrets themselves are stored in the cloud, you can actually change them at any point. So what were static secrets that you could only change by republishing the app become dynamic secrets. So if they get changed for other reasons, or they're breached in some other way, then you can change them on the fly, and literally 5 minutes later, all the apps that are running will be using the new version of the secret. And the quick start integration provides a kind of simple and straightforward way to do the integration with your existing mobile app. So with that, I will hand over to Skip, who is going to kind of do a demo of how this works in React Native app.
Hey, Richard. Well, just before Skip starts, there is a question, but I think you just answered this. It's are these API keys encrypted within the code? And I think the answer is, first, they're not in the code. So you want to just quickly answer that?
Yeah, so they are, they're not in the compile code, so they're not in the app at all at the time the app starts running. And then they are transmitted in a kind of heavily obfuscated way when they're communicated down to the app, only stored in memory in this obfuscated fashion, and only appear when doing the network request, where we've already sort of determined that the environment seems okay.
Okay, thanks.
Okay, does everybody see some code here, Richard? Have
Yes.
I taken over the screen? Great. Okay, so I'm going to attempt to do a live demo, which is always risky. So if it goes kaflooey or I swear too many times, I'm sure we'll re-record this. So when you get the recording, it'll be a clean view, but we'll see how it goes. So what we're going to do today is take a vanilla app. It's actually kind of accessing a movie database. It's written in React Native, and I'm just going to go ahead and run this now and get it building. So we've just started from a vanilla React Native environment. We're making API calls using React. We're using Axios on top of Fetch in this case, which you can see here. We've used fairly good practice in terms of we have a .env file that is not hopefully going to go up to a repo. So this is not going to be exposed to the public, though these strings are going to be in some fashion pushed into your app and will be possibly extractable from the app itself. So this is actually the API key here, and that'll get stuck in. What we're doing right now, if you look at the Metro bundler, is we've launched the app, but it's still uploading all the additional code here. So the app is called Preflix. It's directly connecting to a public movie database, the MovieDB. Their version 3 interface has a query parameter called API_key, and that's what we are using with this API key value right here. And then this has no approve in it at all right now. So once it finishes loading, hopefully we'll see some pictures of movies. And while I'm doing that, this is what a typical, okay, well, it looks like we're going to go now. And there we go. So it's just kind of a simple movie browsing kind of app. So it's showing you what the current popular movies are right here. You can scroll up, and if you want more information on a movie, you click on it. You can search for movies. So we're going to start by searching for Android. Since we're running today on Android, we could be running on iOS as well. And we'll go ahead and search that. And we're going to come up with various Android movies, as you would expect. So pretty straightforward basic app. So we'll go ahead now and start to add approve. So if you were just coming in, the first thing you would want to do is go to the approve website. And by the way, if you're watching this webinar and you haven't signed up yet, please click on that link and go register. So in this case, you want to go ahead and sign up for a free trial. So you can click either any of the free trial buttons in the header or try approve for free. You simply give your name, your address, whatever information you think we should know about your application. No credit card, no nothing. You just sign up, and within a few minutes, we'll have your account set up, and we will issue an email with the credentials you need to get started. This is actually the configuration string used to initialize the SDK. And then this is the initialization string that gets your account onboarded for you so that you can start using the approved CLI. So you've got your account, you're good to go. The next step would be, as Richard said, to go look at the quick starts. We'll go ahead and pull those up in our resources. Because we are doing third-party API or secret protection, we're only interested in the mobile quick starts. There's no need for any backend API quick starts or anything else. So as Richard mentioned, these are usually keyed to specific networking stacks. So for example, on Android, you have all these common retrofit or OKHTTP, Volley, whatever networking stack you're using, we can help support you on that. And so we're using React Native today, and that's built into the React Native stack. So here's the quick start, and you go through and it'll basically explain what to do. So the first thing we're going to want to do here is go ahead and install the Approve React Native package. So I'm going to go over to my main here, and I will do a yarn because I like yarn rather than npm add at approve. /React Native approve, and that's the package. So we'll go ahead and add that. And I must have typed it wrong. 3 P's in approve, what do you know? Okay, so let's try that this time. Okay, so now we're downloading the package, and this includes the SDK. So the SDK in essence has been added to this, as well as some convenience functions and all the control that you'll need to do this. So continuing on, this explains how it works. We're doing secrets protection today. So basically be following a script like this tells you what to do. So the first thing we're going to want to do is well, I guess I should say we're really trying to do 2 things. One, we're trying to lock down the channel between the app and the backend to stop any kind of man-in-the-middle attacks. And 2, we're basically trying to get the API key out of your application, so it's not there at rest, and it's there only when it's needed to make the API calls through the SDK, and not really in the runtime itself. So we're going to first make sure that I have my approve account going. I'm going to be this account today. So I'm just going to switch into this account. And I want to see if I have any APIs currently protected. And I do not. So, oh, it's asking me to enter my password, sorry. All right, so I have 0 API domains. So I'm just going to go ahead and follow the script here. So one of the first things I'm going to do is to go ahead and turn on the pinning. So we're going to want to get that set. So I'm just going to do that right here. I wish it was harder, but that's all you have to do. So now we're using the managed trust routes that Richard spoke about. So whereas before you could defeat the pinning by going in and poisoning the device trust area, here we've now locked these into the app. So you're pretty well locked down. I just need to type yes to confirm it, and we're all set. So after that, the next thing to do is actually add the API itself. So I'm going to go ahead and do that. And I'll do that again using the command line tool. So we're adding the API. And again, it wants me to be careful. So we've now added that. So if we do an approve API-list now, we should see that that's protected. Okay, so we've got that API. So approve is aware that that's a special domain that we want to look after. The next thing we're going to do is we're working with the secure strings capability. So we want to make sure that's enabled. So we'll go ahead and approve and set that to be enabled. Again, it's asking me to type yes. So that's now updated and ready to go. So I think we are in good shape. Let's see if I missed anything else. Oh, of course I did, yes. So the other thing we need to do is to go ahead and add our API key off the device. So we're going to actually add that into approve. So I'm adding it here as a placeholder value called the movie database API key value. And this is the value, which was the same one if I actually do this and send it, you can see that that's the working API key. Here's a valid response here. So that's been added to approve. So as soon as we enter that, it's again going to want me to type yes. And we've now completed that. So at this point, we've got the SDK loaded and we've have the API key stored inside approve. We now need to make a few changes to our environment. So at this point, we no longer want the key to be actually stored in the application itself. So I'm going to change that to my placeholder name, which, as we said, was just TMBD API key value, the same thing that's stored up in approve. And then because I need to initialize the approve SDK, I'm going to add the approve configuration, which I received in my onboarding email right here. So that's this string. You could also get it by accessing it through the approve command line interface. So I'll go ahead and do that, save that. And then the only other step I need to do is actually take the existing app here, which really is just a container for the navigation screens. And I'm simply going to wrap that with approve. So I'll go ahead and do that. So I've wrapped it with approve using the approve configuration, which I set in the environment. And I'm asking it to substitute the query parameter, which is TMB API key name. So I'll save that. So we've now wrapped it with approve. And if I guess I should come clean and show it to you that I got some sort of error, which is interesting. So let's see if we can figure out what's gone wrong. So everything looks reasonable. Sometimes React Native gets in this kind of funny state. So let's just clear this. Oops. It's going to let me clear this. Come on, move over. All right, well, it's definitely misbehaving. So let's just try and force a quit here. All right, let's see if that still has not worked. Okay, I am really stuck. Let's see if it just works. No, okay. All right, so I'm pretty much panicking at this point. Let's see if we can close it this time. No, you gotta be kidding me. Okay, of course it worked half hour ago. All right, well, under pressure, let's try one last thing here. Let's go ahead and reset the bundler. And let's go ahead and rebuild the app now. Okay, let's see if we can kickstart this thing. So you for sure know this is a live demo since we somehow crashed here. And if you have any experience with React Native, you know that there's a lot of caches here trying to speed up the developer experience. They sometimes get out of sync and lock up. So you're probably familiar with taking the bundler and resetting it as you go through. So we are rebuilding here. And George, were there any additional questions that have come in?
Let me see. There is actually one. So yeah, there's a few here. So if an app request comes from a rooted or jailbroken device, does that automatically deny the JRT? And if the app is denied by approve once, is it logged by approve and automatically locked out going forward? So there's actually two questions there. The first one is, about the is it automatic that the denial takes place? Maybe you want to talk a little bit to that it is configurable.
Yeah, so yeah, it depends on the security policy configuration that you have. So the default position would be that a rooted or jailbroken device would not be valid, but you can make it valid, and then you're relying on detection of other feeder and other hooking frameworks, etc., to defend the app. So you are reducing your security posture a little bit, but you can do that. We don't. There are mechanisms that individual devices can be banned, so there are capabilities to do that. But as a matter of course, we wouldn't do that. So normally we take each attestation request as a sort of independent event and evaluate it independently, and don't persist the results. But there are capabilities to do that.
Okay, so we are back. I discovered my obvious and embarrassing mistake that I did not import the approved provider in. I forgot to uncomment that. So We've now uncommented it, so the approve provider is actually being applied. And if you look at what's going on here, here's the original TMB API calls, and you can see they had this string in here which could be intercepted. The new string, when we change the environmental variable, has now that the API key value is just a placeholder here. So when the system goes to run, it comes through and we're getting a failure error from approve saying we've rejected it. And what that means is that, yes, this application has the approve SDK and it's trying to communicate to approve, but as far as approve knows, it's never seen this application before. So the one last step we need to do is actually register this application with approve so that approve can recognize it. So this is kind of akin to if the device was rooted. If the device has been tampered with, approve will say, I don't recognize this, it's not authentic. So in this case, we just need to give the application a registration to do that. So I'll go ahead and add that. And I'm going to run register Android. This is just a convenience function that will register the app for an hour. Okay, so we've registered. It's now passing through all the clouds since Approve is in the cloud all over the world. So I'm going to go ahead and relaunch this app if it's going to let me this time. There we go. Okay, so I'll go ahead and launch the Preflux app. So this now has Approve embedded in. The registration hopefully will have passed through the cloud. So it's now running up and there we go. So now what you're seeing, if you look at the logs, is we are still only using the placeholder key value. Approve is now initializing properly since it has a clean provider. And then approve, once it's initialized, indicates it's ready. We've done just a pre-check pass. That's just additional, just safety check here to see if we're okay. And essentially what as Richard said, what these API calls are now free to run, and the placeholder API key value is being substituted with the actual API key, which is not on the app anymore. It's only up in the Approve cloud. So we can kind of test that by taking the existing Approve setting and just change the key on the fly. So if this was the original key, and let's just add 3 X's to it to make it an invalid key. So I'm now pushing this to the Approve cloud. It's telling me to be careful. I pushed to the cloud. So now this is, in a sense, imagine that the API key has changed. So I'm again going to just stop the app here and relaunch it. And if we now run it, we're seeing it's now failed. So in essence, what it's now doing is substituting in, it's going to the Approve cloud. It's saying, yes, I'm a valid app. Give me your API key. The key that's actually given has this additional XXX in there because we changed it. So on the fly, we've actually changed the API key going into the app. We actually did it wrong. So we actually broke the connections through. So if we want again to go live, we could just go ahead and update this, and that'll push now a new API key into Approve, which will then on launch get, and every time the API is checked, we'll go ahead and update that key on the fly. So a lot easier than actually upgrading your app with a new static API key and pushing that into the Play Store and trying to get everybody to upgrade to the new version. So I'll stop here just on time in case there are a few additional questions.
Okay, thank you, Skip. So we have another question here, and it's actually, maybe if you want to take a look at it in the chat, a question around the encryption key, and that the key is not persisted on the device, so they can't gain access to local data until they authenticate. And then it says, is generation of a second asymmetric key possible? And so that's the question. As you got any thoughts on that?
Is this with respect to sort of app instance strings?
Yes, yes, it is.
Yeah, so currently it's a symmetric encryption key, because all the encryption and decryption is actually done on the device itself. So the actual values that are being held securely are held in persistent storage on the device. It's just the key is not held on the device. So the key becomes ephemeral and held by the approved cloud. And so the decryption key is only available if the app passes the attestation mechanism. I mean, I guess that could be a future extension to provide asymmetric keys to separate the encrypting part from the decrypting part.
Okay. And then there's another question, which is, what's the difference between this and OAuth? It seems like Approve is the authorization server, and it uses a proprietary authorization access token request setup. So you want to answer that?
Well, I think with Approve tokens, yes. I mean, there are similarities there. I suppose, as I sort of said at the start of the presentation, the problem with simply using user authorization is it's not authenticating the app. So in public clients for OAuth, generally the recommendation is not to use a secret, although secrets are still used. But the problem, of course, well, if you don't use a secret, then you're not actually authorizing the app at all, and therefore anyone with valid user credentials can make an OAuth request and get a valid token. So one of the things we are looking at in the future with integrating with OAuth is to use dynamic client registration. So there is a mechanism inside OAuth that is essentially to solve this problem, which is to properly attest the client prior to giving a user authorization token. So that's some sort of interesting potential that we're looking at, and we'll release demos in the future of how to use this capability to leverage against dynamic client registration.
So watch this space for a new release, right?
Yeah, so one way I just kind of look at this broadly is that user authorization and application authorization or authentication are very complementary. So when you use something like OAuth, you're really trying to identify who is actually going to be using the app and making your API calls. And with Approve, you're doing a similar thing, but you're basically trying to determine what is being used to make the API calls. Is it a clean, authentic app that hasn't been tampered with running on a safe device, or is it some bot somewhere or some other tampered device? And the two actually can be bound together in the Approve system, so that you really need to pass both in order to get through to an API call.
Very good. So there is another question, and Richard, if you want to pull up the last page of the presentation as well while I'm reading this out. If the API is using JWT token, does the API need to go through TLS connection or one, or does it have to have two TLS connections, or is one TLS okay? A one-way TLS okay? Do you understand the question?
Yes. So my understanding of the question is you do not need mutual TLS in order for this scheme to work.
Okay.
And you also should understand that the Approve system is not in the API calling path. It's off to the side. So you use Approve to do the attestation and to get served a valid or invalid token if it's failing. And when you go ahead and make these connections, and when you're pinning these connections, it's just a one-way TLS connection. There's a handshake back and forth, but you're basically authenticating that the end device that you're calling to is what you're expecting using that one-ended TLS.
Yeah, exactly. It's not mutual TLS, because the problem with mutual TLS, it has its advantages, but ultimately then the certificate on the client side just becomes another secret. So you could in fact use the Approve secrets capability to pass a certificate to do mutual TLS. But that's not the way we would normally recommend doing it. That's not how the quick starts do it.
Okay, there are a couple more questions, and we'll find a way to answer those and get the answers out to you. I'm conscious of the time. It's 2 minutes past the hour. Just to complete today's webinar, we wanted to make this offer to attendees. As you probably saw, it's very easy to set this up, and we're offering a 30-day trial period. No need for any credit card, completely complimentary. And for a limited time, for the first 5 people who sign up for a trial who attended this webinar, we're going to additionally offer a pre-deployment check. Checklist review, and that will cover a number of things, including security policies, your front end and your back end implementation, the pinning, the testing strategy you're using, as well as really digging in deeply into your environment and helping you get the trial set up so you get the maximum benefit from that. So use the code when you sign up for a trial, and we will make sure that we provide that extra value for you. At this point, I think we're done. I want to thank the panelists and particularly Richard and Skip for preparing this presentation. And we will make the recording available, and we'll send you a link so you can watch it at your leisure. Thanks a lot, everybody, and the webinar is now complete.
Okay,
Thank you.